Today in Capechi's Corner, we're going to look at circles and lengths of segments. The first theorem today states that when two chords intersect inside a circle, the product of the segments of one chord equals the product of the segments of the other chord. So we have R times S is going to equal T times U. In the second example, that's what we have. So we have 6 times 8, because those chords are intersect inside the circle, is equal to 3x times x. So that gives us 48 is equal to 3x squared. I want to get x by itself, so I have 16 is equal to x squared. Now when I take the square root of both sides, I actually get plus or minus 4 is the value for x, but I know in my diagram that x has to be a positive value since it's a length. So in this case, x can only equal positive 4. Now I can check my work saying this is 4, and this 3 times 4 gives me 12. So 4 times 12 gives me 48, and 6 times 8 also gives me 48, so I know I have the correct value for x. Our next theorem states when two secant segments are drawn to a circle from an external point, the product of one secant segment and its external segment equals the product of the other secant segment and its external segment. That is really wordy, so I like to say that the whole times the outside is equal to the whole times the outside. It's a little easier to follow that way. So if I look at my given example, this first secant segment out on the top, the whole part is R. The side outside the external part is S, so that's going to equal T times U, T being the whole secant segment and U being the outside. Let's look at the second example. So I have 12, which is the whole secant segment, times the outside is 5, is equal to the whole secant segment is x times the outside is 6. So it gives me 60 is equal to 6x, so x is equal to 10. Now again, I can double check my work. 12 times 5 right here gives me 60, and then the whole thing here is now 10. 10 times 6 also gives me 60. Our next theorem is similar, but instead of two secant segments, we're looking at a secant segment and a tangent. So it states when a secant segment and a tangent segment are drawn to a circle from an external point, the product of the secant segment and its external segment is equal to the square of the tangent segment. So in order to remember, I like to say the same thing again, the whole times the outside, and we're going to multiply two things. In this case, we don't have a whole and an outside, we just have an outside, the tangent. So I like to say we actually multiply that twice. So then when we do that, we have whole times the outside is equal to the tangent squared. So a lot of students forget to square and they just use the tangent value itself, so we have to be careful. So in our first diagram, the whole is R times S is equal to our tangent squared. In our second example, we have the whole part of our secant segment is 20 times the outside is 4, and then my tangent is x, so I'm going to square that, so I have x squared. So I have 80 is equal to x squared. Take the square root of both sides. Now again, I remember that my x value has to be positive. The highest perfect square that goes into 80 is 16, so I have the square root of 16 times the square root of 5 is equal to 4 root 5 has a value of x. Now again, I can check that. I know 20 times 4 gives me 80. So if I do the same thing, 4 root 5, and I square it because that's my tangent, that's the same as 4 root 5 times 4 root 5, which is 16 times 5, which is also 80. So I know my value is correct. Let's look at some more examples. So in this diagram, I noticed that my radius is 6. So I'm going to make this 6 on the other side. I'm looking to find the value of x. Now the chords intersect inside, so I know I need to take the product. So I have x times x. That's for this chord right here. And when I look at my other chord, I have to be careful because really part of it is 6 plus 3, which is 9. So that is going to equal 9 times, and the other part of that chord is 3. So that's a tricky one. So that gives me x squared is equal to 27. Take the square root of both sides, and again, I know that x has to be positive since it's a length of a segment. So x is equal to the square root of 27, which can be simplified to the square root of 9 times the square root of 3. So x is equal to 3 root 3. In our next example, we're asked to find the length of BP. So I'm going to make that x. That's my unknown. Now, I know that this whole chord AB right here has a measurement of 12, but I don't know what the pieces are. So I'm going to make BP is equal to x. So then AP is actually going to equal to 12 minus x, since I know that that whole piece is 12. I'm going to multiply my pieces of my chord there. So I have 9 times 4 is equal to x times the quantity of 12 minus x. Now I just have some algebra. 36 is equal to 12x minus x squared. Anytime I have x squared, I'm going to bring everything to one side. I want my leading coefficient to be positive. So I have x squared minus 12x plus 36 is equal to 0. And now I'm going to factor it. So I know my signs are the same. They're both in negative. So I have x minus 6 and x minus 6. So x is equal to 6. I go back to my diagram, and I realize that x does have a value of 6, and that's the measurement of BP, which is what the question's asking. So BP has a measurement of 6. The next problem states find the lengths of segment PT and segment PC. So I'm going to make segment PT is equal to x, and PC, the whole piece, I'm going to just make CD equal to y. In the end, I'm going to add CD to PD. So I know that PT is a tangent, so x squared is going to equal. Now, I have measurements for segment AP, so I'm going to use that. So x squared, which is my tangent, is equal to the entire secant segment, which is 10, times the outside, which is 5. So x squared is equal to 50. Take the square root of both sides. Again, I know x has to be positive because it's a length, so the square root of 25 times the square root of 2. So x has a value of 5 root 2. So that's the measurement for a PT. PT is equal to 5 root 2. So we're done that one. Now let's look at another one, the other one. We're trying to find the measurement of PC. So I need to find DC first. So again, I have the measurements for AP, so I'm going to use that. So the whole secant segment is 10 times the outside is 5 is equal to. Now this whole piece, segment PC, has a measurement of y plus 4 times the outside, which is 4. So it gives me 50 is equal to 4y plus 16. I get y by itself by bringing the 16 the other side, and I have 34. So y is going to equal 8.5. Now I have to be careful because that gives me this piece right here, segment DC. I want the whole thing, PC. So I need to add the outside there, PD, to my value there for DC, and I have 12.5 is the measurement for PC. In our last example today, we're asked to find the length of segment PB. So I'm going to make that x. Now I have two secant segments I'm going to work with. So I know AP, the whole segment is x plus 11 times the outside, which is x, is equal to, in PC, the whole piece there is 12 times the outside, which is 5. So I have x squared plus 11x is equal to 60. I'm going to bring everything to one side and see if I can factor it. Now I know my signs are going to be opposite, so I have x plus and x minus. And I'm looking for factors of 60 that when I subtract I get to 11, and that's going to be 15 times 4. My 15 needs to be positive, so the 15 goes there and the 4 goes there. So I have x plus 15 is equal to 0, or x minus 4 is equal to 0. So x is equal to negative 15, or x is equal to positive 4. Now if this were just a regular algebra problem, both of those answers would be okay. But again, since we're working with geometry and we're working with diagrams, I'm noticing on my diagram that PB has a value of just x, so I know that has to be positive. So I can only go with x is equal to 4. So therefore, PB has a value of 4.